the first come first served scheduling algorithm. Now, what is FCFS scheduling algorithm? It is by far the simplest CPU scheduling algorithm. It's because in the word itself, first come, first serve, it means that the process that requests the CPU first is allocated the CPU first. So this implementation is being managed by the FIFO queue. So FIFO means first in, first out queue. Now here we can see that we have here a series of processes: process 1, process 2, 3, 4, and 5. Now they are in queues. So since process 1 comes first, it means that process 1 will be accommodated first by the CPU. So whoever comes first in the queue is the head. We call it the head. Now the last part, or the last uh, one who arrives in the queue, is what we call the tail. Now when CPU is free, let's say for example, there is no process going on around our CPU, it is then allocated to the process at the head of the queue. So by here, this diagram, if this CPU is vacant, there is no processes in it, process 1 will be accommodated by the CPU. And then the running process is then removed from the queue. So here, when process 1 is being processed or allocated to the CPU, it is then removed from the queue. So process 2 now becomes our head, and process 5 becomes our tail. Now, let's say for example that there is another process that will be put in the queue. So it will be placed at the end and will be the new tail. So that is how a first in, first out queue is being implemented. Now let's have an example here. So let us consider the following set of processes that arrive at time 0. So we have here P1, okay, process P1, P2, and P3. Now P1 has a burst time of 24 milliseconds. So it means it takes the CPU to process P1 24 milliseconds. So P2 at the same time have a burst time of 3 milliseconds, and P3 the same with P2, it takes the CPU 3 milliseconds to complete the process P3. Now let us consider uh, these processes arrives in this order: P1 first, followed by P2 and P3. P1, when P1 arrives, the waiting time for P1 is 0. It's because uh, the CPU is vacant, and when P1 arrives, it is being accommodated directly by the CPU. So it has no waiting time. Now when P2 arrives, okay, the waiting time for P2 is 24 milliseconds. It's because process 1 took up 24 milliseconds. The CPU took up 24 milliseconds before process 1 is completed, and then CPU becomes vacant at this time. So that's why P2 has to wait 24 milliseconds before it will be accommodated by the CPU. Now when P3 arrives, okay, the waiting time of P3 becomes 27. It's because 24 plus the burst time of P2 is 3 milliseconds. So 24 plus 3, that's why it becomes 27 milliseconds. So we have a total of 30 milliseconds. Now in order to get the average waiting time for this process, so we have here the total. We have to add up the total process waiting time. So we have 0 plus 24 plus 27. Okay, so we have here 51. Now we have a total number of 3 processes, and then we have to divide that. We get the average waiting time of 17 milliseconds. Okay. Now that is in this order, P1, P2, P2, and P3. Let's have another example. Now let us consider that the processes arrives in this order. P2 first, followed by P3 and P1. Now they have the same burst time with the previous example. Now when P2 arrives, the waiting time of P2 is 0 milliseconds since it is accommodated directly by the CPU. Now when P3 arrives, the waiting time for P3 becomes 3 milliseconds because the burst time of P2 is 3 milliseconds. Now when P1 arrives, okay, so the waiting time for P1 is 6 milliseconds because P2 and P3 has a burst time of 3 milliseconds each. So P1 has to wait 6 milliseconds before uh, it will be accommodated by the CPU. Now, still, since the burst time of P1 is 24 milliseconds, we have a total time of 30 milliseconds. Now, to get the average waiting time for this example, this order, we have we have to add up, okay, waiting time of P1 which is 6, waiting time of P2 which is 0, and waiting time of P3 which is 3. So divide that with the total number of processes. So 9 divided by 3, we get 3 milliseconds. Okay. So with that, we can say that the average waiting time under the FCFS policy is generally not minimal and may vary substantially. So it depends on the order of the processes that it arrives. So it may vary substantially. And once the CPU has been allocated to process, that process keeps the CPU until it releases the CPU. So meaning to say, you cannot hold the CPU while it has still processes on it. So it can only be terminated by other. It can only be released by either terminating or by requesting input output. Okay? So that becomes one of disadvantage that becomes a disadvantage of this type of scheduling since it is not suitable for time sharings because we cannot share the CPU. So since it we have the processes have to wait before for the previous process to finish before it will be accommodated by the CPU. So it is not a recommended technique since it is not advisable to keep the CPU for an extended period. So with that, we can say that uh, FCFS scheduling algorithm is not that good. It's not recommended. So thank you.